Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Mastering Data Structure and Algorithms in Java series. So today's data structure is linked list. It is the part 1 video. So let's start. In this video we are going to discuss the theory on the linked list, and in the next one we'll cover few of the code examples. Okay, so we have covered arrays already for linked list. Let's go through a few of the definitions and understandings. So linked lists are fundamental type of data structures. Why do we call them fundamental? Because majorly a lot of data structures are built upon the understanding of linked list. Unlike arrays, linked lists do not require contiguous memory allocation. We'll come back to this one. So we had seen last time that arrays requires continuous memory location in the memory, right? So one after the other. Linked lists do not require that. They generally save the address of the next pointer in the same node. Like for example, in this node, we have created a simple node. We have data, that is the value of that element, and then it stores the address of another node. Okay, so we'll understand that quickly. Okay, and similarly the next node will hold the address for the next node, and then the next one will have the address for the next one, likewise. A quick comparison with the arrays. Arrays store elements in contiguous memory allocations, allowing for constant time random access. Because since they are in the contiguous memory allocation, we can do the indexing on them, and we can directly fetch random elements at constant time, right? If you want to fetch the fourth element, we can directly do nums of 3. 3 is pointing to the fourth element, because indexing again starts from 0. 0, 1, 2, 3, it points to the fourth element. Linked lists, on the other hand, use pointers to connect two elements, enabling efficient insertion and deletions. So let's look at this point. We'll come to this point as well. Okay. So we saw that linked lists are fundamental type of data structures. Unlike array, they do not require contiguous memory allocation. Okay. Okay. Let's understand linked list here. So just as a quick review, let's say we have not this, yeah, let's say we have these numbers 1, 3, 5, 7. Okay, and first let's say we store them in an array. Okay, so how array will store them is, let's see that this is memory in the system. So our 0th index is here. Let's call it 1000. Okay, so this is our 0th index, 0. So this is 0th index, this first index, second index, third index. It will have the value 1. Then right next to it will have the value 3, then 5, and then 7th. Okay, again this is index 1, this is index 2, and this is index 3. Okay, now if I want to fetch the first element, let's say the array was given the name as nums. So if I want the first element, I can simply say nums of 0. If I want the third element, I can say nums of 2, right? That will fetch me 5, nums of 2 on the second index. This is how these numbers would be stored in an array, right? Now let's go back a little. Okay, let's see how will we store them for linked list. Okay, so linked list, as the name suggests, they are linked. First, let's look at their memory allocation. Okay, if 1 is stored here, so we'll have 2 sections to it. Okay, first section would be the data section. This is where the value is stored, 1 is stored, maybe its address is, let's say, 1000. So this is where we are starting the linked list. So start of the linked list, we have a head, so it's like a pointer. So pointer pointing to the first node. Okay, Now their second partition is empty as of now, let's say, and so generally it has a null to indicate that the end of the node or end of the linked list. But now we have 1357, so it will store the address of some other node. So let's say here we have our second node. Okay, its address is 2000, so here we'll have the value 2000. So from here we can directly jump to the next node, and in this we have stored the value, that is 3. Again we have one more node somewhere. Here we have the data, that is 5. Again one here. Here we have the data, that is 7. But then this node's address is, let's say, 7000. This node's address is 4000. So the previous node, this one 3, will store the value, that is 3, and the value of the address for the next node. So it will store 4000. Similarly this one will store 7000. So this one can link us to the next node, and this one can link us to the next node. Now after 7000 we do not have any other node that is attached, right? So this one will have a null value. Okay, this one will have a null value, or we can do it like, okay. Now what happens is, if we want to insert any element after 7, let's say we want to insert an element 8, okay, what can we do? We'll create another node somewhere. Maybe in this complete memory location we created another node. Node will have two partitions. One, this one will be for data, so that will have the value 8. This one is already null because only a node is created, right? But now we are adding it to this linked list. So how do we add it as part of this list completely? So this previous node 7 was pointing to null. Now this one will have the address of this node. So let's say this node has the address 5000. So we'll insert 5000 address here. Now this can point to this node. We can get the value 8, and the next is null. Okay. Now let's do one more thing. Okay. Now again we'll take the same example. There was 1 3 5 7. Okay. Now when we talk about linked list, we always discuss them like this. Okay. So first we saw how they are treated in memory. Now we'll see how they actually look like. Okay. So we have these nodes. Okay. So this one will have the value 1 3 5 7. This one points to the next. This is how we represent a linked list. Points to the next, points to the next, and the last one is null. Okay. If you see here in this example, we have seen that a node will have data and then pointer to the next node again of node type. So you can see it's a pointer to the next node, right? So we have data of integer and then pointer to the next node. As we saw in the memory, this actually has the address for the next node. Now let's imagine and now let's compare it with an array. Okay. Now before comparing it with the array, let's do how let's see how will we traverse through this array, traverse through this list. Okay. So for an array, what we were doing is we were running a for loop. Okay. And then one by one we were going to the next index and we were doing I++, right? But in this case, we have one starting pointer that we'll call it as head, pointing to the head, and we traverse this value. Then we simply mark, let's say we create another pointer, temp is equal to head. Okay, so now our pointer temp is pointing to the same location where head was pointing. We can get the value like temp.data, this will fetch us the value. So we can give int a is equal to temp.data. So we'll get the value 1. Then we want to move forward. So we'll say temp is equal to temp dot next, right? So now temp will point to temp dot next. This is the next, as we saw here. This is the next, right? So temp will get the value of temp dot next. So now temp will point to the next, because next is pointing here, right? Earlier head was pointing here, so temp was pointing here. Now we do temp is equal to temp dot next. Temp got the value of the next pointer, that is here. Now again we can get the value like int b is equal to temp dot data. Again we move forward, we do the same command, temp is equal to temp dot next. This is next. So temp is here, temp is equal to temp dot next. So temp points to this one. Similarly to this one. And then for arrays we used to keep a loop something like this. Int I is equal to 0, I is less than array dot length. Let me write it in a little better manner. Okay, for arrays we used to do it like for int I is equal to 0, so I would be the starting index, I is less than array dot length I plus plus. Okay, and then some code. Here this initialization we are doing it with temp is equal to head, so temp gets the head. I plus plus we are doing with temp is equal to temp dot next. But this condition, which actually helps us in avoiding array access out of bounds, we do this by checking every time that temp is not equal to null. Before fetching the value something like int c is equal to temp dot data, we'll check if temp is not equal to null. Now every time when we did temp is equal to temp dot next, we reached 5, then we reached 7, and then in the next temp dot next it reached the null. Now before assigning the value, every time we keep a loop. So if temp is not equal to null, then we can say int c is equal to temp dot data. So it will get the value like this, right? Now the question is, we used to do the same with the arrays, and now for for linked list also we are using the same technique. Okay, it's slightly different, but overall principle is same. Now let's look at it one more time to understand it on a deeper level. Okay, so again we'll take the same example. Oops, what's happening? Okay, one, 3, 5, 7. Okay, let's say I want to print this. Okay, let's say for an, how will we print it for an array? First let's see. If we were storing it for an array, we'll print it something like this. For int I is equal to 0, I is less than array dot length I plus plus, then system dot out dot println array of I, right? Now how will we print for this linked list? Let's see, linked list. Okay, let's say we have the print method, print list. We could have created the same above this as well, so it doesn't make much change. Now node temp is equal to head. Okay, we'll create a linked list here. 1, 3, 5, 7. This one is pointing to null. 1 is pointing to 3, 3 is pointing to 5, 5 is pointing to 7, and head is pointing to the head pointer. Now we are saying node temp is equal to head, so temp will point to the head. Now before printing the value, every time we want to check while temp is not equal to null, because if it is equal to null, like it would happen in the last case when it goes to temp.next, it will reach the null in the end. That time it does not null does not have any value, right? So we do not want to say fetch the next value, so we want to avoid that. So that's why we do a temp is not equal to null. This is the same check like this one to keep it from array access out of bounds. So we'll say system.out.println, and we'll print the value like temp.data. And then what will we do? We'll move the pointer. Here we'll move, we were moving the pointer using I++. Here we'll just say temp is equal to temp.next, right? And this is next, and this is data. So each node has data and next. So when we say temp.data, it fetches the data, prints the value 1. Then we do temp is equal to temp.next, temp moves next. Then again, is temp not equal to null? Yes, it is not equal to null. We print temp.data, temp.data is 3. So first 1 was printed, then 3 is printed. Then temp is equal to temp.next, it moves to next. Then 5 is printed, it moves to next. Then 7 is printed. Then we say temp is equal to temp.next, it moves to next, which is null. We say is temp not equal to null? No, temp is equal to null. So the loop breaks here and we come out of the loop. Okay. So this is basically the linked list, or how the linked list overall works, right? Now let's do one thing. Let's discuss linked list on other levels also. Okay, so we know that as a node, this is what a node is. We have data here and we have next here, which points to the next one. Okay, from the code perspective, we can see we create a separate node, we give the data, we have the next. When we initialize another node, we just initialize the value and mark the next as null. Okay, when we connect them to the next node, that is when we connect to that this node dot next pointer will point to the new node. Okay, one of the operations is insert, where we add 1, then 3, then 5, then 7. So we'll do something like this. We'll say insert int data. First we'll create the data, so we'll say node. Now if you see, node is this node class, the node data structure, the node class. Okay, we'll say node new node is equal to new node, and we'll pass the data. So let's say if in the beginning 1 was passed, so a new node is created that has 1, and what is its next pointing to? The next is pointing to null. This is the constructor. You can see in data, this dot data is equal to data, this dot next is equal to null. So it is pointing to null. Then we can say node dot next is equal to head. Okay, now we are saying node dot next is equal to head, so we had a head pointer, so node's next will point to head. Okay, and then since this was the first value, we want the head here, so in the end we'll say head is equal to new node. Now what will happen? Let's delete this part. Okay, so we have something like this, that we have 1, the next is null, and this is head. Next time we insert the value 3. So we int data is equal to 3. We create node is equal to new node. A new node is formed. It has the value 3. The next is null. We say node dot next. So this node dot next is equal to head. Right? So its node dot next would, instead being null, it will point to head. And then head is equal to new node. So head will then point to new node. So it will become something like this: 3 pointing to 1, and then 1 is pointing to null, and head is now pointing to 3. This is that we are inserting the data in the beginning. Similarly, you can insert the data in the end, where each time you create another node and you say head dot next is equal to new node. So every time we'll get the next node. Now, or you traverse the previous node, you keep a last pointer and the next of it is the next node, or you enter them in the reverse order. So you can always create a node. In the end, it will always happen like you always create a node, there is data, this one is pointing to null. Now you already have a list that is created, that is already working fine, and you can directly map it anywhere. Okay, if you map this data to this one, it will directly point to this one. You map this data to here, it will get inserted in the middle. So we'll come to those operations as well. Okay, okay, let's do one thing again. Okay, let's move forward. So linked lists use pointers to connect elements and enabling efficient insertion and deletion operations. Okay, let's look at the insertion and deletion operations on linked list and arrays. So we have 1, 3, 5, 7, and we want to insert the value 4 in the middle of this. Now, how will it happen for arrays? First, let's discuss for arrays. Now, arrays in memory, they are stored in contiguous memory location. Okay, 1, 2, 3, 4. So we had only 4 slots here. Now we want to insert 4 in the middle, right? So what do? We create another array of size 5. 1, 2, 3, 1, 2, 3, 4, 5. And then we insert one by one. We insert 1, then 3, then 4, then 5, then 7. Okay, if you see, this is very tedious process. So you have to create a new array with new size, and then previous array will be deleted. Previous array will be deleted. Okay, so if you see, insertion is quite difficult here. Of course, fetching the elements, getting the elements is easy for arrays. For linked list it's difficult. We have for linked list, the only possible way is to traverse. So we have 1, 3, 5, 7, and I want to find out the third element. So I have to go one by one. I go to 1, I keep a counter, this is my first element, then go next, this is my second element, then go next, this is my third element, I print 5. Here for arrays, if I want the third element, I can directly say array of 2. That's it. But for insertion, it is very difficult to insert in arrays. But how will it happen for linked list? Okay, let's see how will it happen for linked list. And this is one of the very famous reason why we have the linked list data structure. Okay, so for linked list, we had 1, we had 3, we had 5, and we had 7. 5 is pointing to 7, 3 is pointing to 5, 1 is pointing to 3. Now we want to insert 4 in the middle of 3 and 5. So we'll create another node 4. Another node is created. Simple. We'll say 4 should point to the next of 3. So whatever 3 was pointing to, 4 dot next would be 3 dot next. So this will point to 5 and will point 3's next pointer to point to 4. Simple. We didn't have to break the list. We didn't have to create new one. Plus in memory, if you see, let's say 1 was stored here with this address, the next pointer, 3 was stored here, 5 was stored here, 7 was stored here. Now 4 is created here. We are just saying 1 points to 3, 3 points to 4, 4 points to 5, 5 points to 6. So 5 points to 7 and 7 points to null. So what will happen? This path will get deleted and 3 will point to 4. This will get deleted. 4 will point to 5, 5 will point to 7. So insertion was very simple for a linked list in comparison to arrays. Similarly, deletion. Now let's say we want to delete 3. So what will we do? We'll for arrays, we'll create another array. We'll create another array in the memory location of new size, that is 3. Then we'll store 1, 5 and 7. What will we do in case of, so again this operation would require new array with new size and then previous array getting deleted on its own. Oops, I deleted. Can I get it back? Oh no. Okay, I'll create it again. This is 3, this is pointing here. Okay. Now in this case, if we want to remove 3 now, let's imagine this is not there. Okay. 3 was pointing to 5. Now we want to remove 3. What will we do? 1 will directly point to 5. And then since there is no pointer pointing towards 3, in the end 3 will get garbage collected. So 3 will automatically get removed and 1 is directly pointing to 5. So it was very easy for linked list. So insertion and deletions are very easy operations with linked list in comparison to arrays. Searching of elements is very easy in arrays in comparison to linked list. Okay. With this, let's move forward. Okay. Now, when we discuss linked list, there are several types of linked list. So one is singly linked list. Singly linked list consists of nodes where each node contains data and a reference to the next node. The one that we have been seeing right now in all of our examples. So okay, let's just go through the types and then we'll understand them with the approach. Okay, so insertion and deletion at the beginning of the list are constant time operations O of 1, while insertion and deletion at the end of the linked list are linear time operations O of n. Okay, I'm not sure if you guys are familiar with the time complexity and space complexity, but I'll make another video on that one. But for now, let's understand. So we have this link, we have this, why is it not typing? Okay, we have this linked list, right? We have 1, I'll write it 1, 3, 5, 7, pointing to 3, pointing to 5, pointing to 7. So this is singly linked list. It starts with a head, ends at a null. So you can start, you can go forward as long as you do not detect a null, and that's way it's a singly linked list. If you want to add any node to it, as we discussed, we add a node, new node, let's say 0, and I'll mark 0.next. So this new node dot next is equal to head. So this will point to head, and I will say head is equal to new node, as we saw in the examples earlier. So now this will become our head and a new list will become 0, 1 3 5 7. Similarly, if I have to delete in the beginning of the list, so adding at the beginning of the list or deleting at the beginning of the list, for deleting I'll simply say head is equal to head dot next. So head will directly point here, so this will become a new head. This one will automatically get out of the list, so we'll have the new list here as 3 5 7. So it's very easy, right? It's in the beginning, so it's a constant time approach, so it's O of one time complexity, that is constant. Every time it will take the same amount of time. But imagine that we have to insert a new node at the end of the linked list. Okay, so we have one. Okay, now we want to insert a node here. We want to insert a new number, that is 8, at the end of the linked list. So what will we do? First we'll do a traversal where we create a temp which is pointing to head, then we do temp.next.next until we reach the null. Then we can say a previous pointer that we have, we'll call it, let's say, or we'll directly check if temp dot, let me write it again. We'll directly check while temp dot next is not equal to null. Only then the loop will break. So instead of checking temp.next equal to null, temp equal to null, we are checking temp.next is equal to null. So when temp reaches here, we know its next is already equal to null. So now we can say when this condition happens after this, or we'll create it as if loop. So if temp.next is equal to null, and we are already doing outside temp is equal to temp.next. So we can say temp dot next is equal to new node, right? The new node that we had created. So when we did a new node was created with the value 8. The next is already null, but now we are saying temp dot next. So we are temp is at here, temp dot next is equal to new node. So 7 will now point to 8 and 8 will get added. But what was the time complexity of this operation? We had to traverse the complete linked list. And how many elements are there? You can consider there n elements, let's say. So what is the time complexity? O of n. Similar fashion, if we have to delete the last element, right? We go for temp.next if temp.next equal to null. So when we are here, temp.next is equal to null, we directly here say temp is equal to null. So we'll mark this as null. Okay, so next of the previous node equal to null. But again, in this also we have to traverse the complete list, right? So insertion in the beginning of the list on the head, or deletion in the beginning of the list is constant time, that is O of 1, but insertion and deletion at the end of the list is O of n, time complexity. Okay, let's move forward. And this is singly linked list. Okay, singly linked lists are useful when frequent insertions and deletions are performed at the beginning of the list. That is understood, right? Let's move forward. Second type is doubly linked list. So doubly linked lists are similar to singly linked lists, but each node contains a reference to both the next and the previous nodes, enabling us with bidirectional traversal. Okay, so to understand the example here, okay, this was singly linked list. Okay, singly linked list where we have data and pointer to next. Now in doubly linked list we have something like this. We have the data in the middle, we have two pointers, one is to the previous and one is to the next. So if we have a list something like this, 1 3 5 7, we'll have something like this. 1, or let me create it here. Okay, so we'll have 1, 3, 5, 7. The next of 7 is null. The previous will point to 5. 5's next points to 7. 5's previous points to 3. 3's next points to 5. 1's next points to 3. 3's previous points to 1. And this is head, and previous of this is null. Okay. Now this is what happens with a doubly linked list. Doubly linked list we can traverse in either direction. So let's say we are at the node, we are given the node 5. We can check directly which is the previous element, and similarly we can check which is the next element. This is generally helpful. Let's say you have a question, something like this, that delete element or delete node previous to 5. So what will you do in this case for a singly linked list? For a singly linked list we have this approach, right? We want to delete 3, but how will we delete? We start the traversal from 1. The question says delete the node previous to 5. Then we go to 3, but we still don't know that we have to delete 3. Then we go to 5, and now we know that we are supposed to delete the previous node, right? So this makes it difficult for us because we cannot jump from 5 to 3. There could we could have used several approaches, like keeping counter. Like at 1 the counter was 1, at 3 the counter was 2, at 5 the counter was 3. So we do our traversal again, and now since the counter is 3, we have to delete a counter minus 1 node. So next time we come 1, we come 3, counter is 2, we delete this node, right? But again, while deleting this node, what do we want? We need a pointer to the previous node to point it to the next node, right? So we have to store it separately, creating another pointer, and at each state we update the previous pointer as well. Similarly, other approach is directly that from the beginning you keep a previous pointer. Let's say previous pointer you are keeping as temp. The next moves to temp is equal to temp dot next. So temp keeps moving, and the previous one is still pointing to the last temp. When the temp moves to 5, previous would move to 3. And then when you get the value 5, you can say from the previous one that we can delete this one. But it's much easier when you have a doubly linked list, because with doubly linked list you go 1, you go to 3, you go to 5. Okay, you got 5. We want to delete the previous node. So what will we do? We'll say 5, like this node, let's say this node is temp dot previous. So temp dot previous is equal to temp dot previous dot previous. So we are saying temp dot previous should point to previous dot previous, and then temp dot previous dot next is equal to temp. So we are saying temp dot previous next should be temp. So we can directly change the pointer to point from 1 to 5, and from 5 to 1, and 3 will get out of the list, right? So this is one of the benefits for doubly linked list, and this is how a doubly linked list is made. One more thing, when we declare the class for the node for doubly linked list, like we were doing it for a singly linked list, we'll do it something like this, where we create a node class and we say int data, then we have node previous and node next, and similarly we will have our constructor node int data what will we do? This dot data is equal to data, and previous is equal to next is equal to null. Okay, for singly linked list we didn't have the previous pointer here, so we didn't need it here. For doubly linked list we have the previous pointer and the next pointer. Okay, let's move forward. Also, doubly linked lists require more memory due to their additional requirement for saving the pointer to the previous node as well, right? Third type of linked list is the cyclic linked list. Okay, so it happens when you have a circular linked list. Okay, cyclic lists are linked lists where the last node points back to the one of the previous nodes, creating a cycle in the list. So it says one of the previous nodes, it need not be the head node again. Okay, let's quickly look at the example. So I'll say command D delete. Okay, so we have 1 3 5 7. Okay, let's see. Cyclic linked list can be in singly linked list or doubly linked list. Okay, so we'll say singly linked list. We have 1, it points to 3, which points to 5, that points to 7. And for singly linked list this was used to be null, right, like this, but now it points somewhere back to other linked list. So if it's pointing back to 1 and we start our journey from 1, we do temp.next, 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 temp.next will get us to 1 again, and temp.next will be in a circular loop, we'll never get the null value. Also it can happen that maybe this points back to 3 or it points back to 5, but in either case we do not have a null pointer here. So once we come into the cyclic loop and we go with traversal while temp is not equal to null, we are saying temp is equal to temp dot next, and temp was initially initialized to head, so this is head. We created another pointer temp, now temp points to head, so temp is pointing here. So temp is not equal to null, temp is equal to temp dot next, temp came here. Not equal to null, temp is equal to temp next, then 5, then 7. After 7, back to 3, then 5, then 7, then 3, then 5, then 7. So this loop will never end, will never end. So this is an example of cyclic linked list. Okay, now let's move forward. Detecting cycle in a linked list. So this is one of the most common interview question, plus it is asked a lot of times whenever we discuss linked list or whenever we discuss cyclic linked list. So one of the solution is you can use a 2-pointer approach where you have a fast pointer and a slow pointer, and if there is a cycle they will always catch up in the same node. We will be discussing them in the part 2 with code examples, but for understanding it's something like this. Let's say let's consider this example only. Okay, so we have 1, it points to 3, it points to 5, it points to 7, and 7 then points back to 3. So what we'll do is we'll create 2 pointers. Okay, we'll call one as the slow pointer, we'll initialize it to head. We'll call another one as the fast pointer, we'll initialize it to head. Okay, or temp already has the value, so slow pointer points to temp, fast pointer points to temp. So right now this is slow pointing here, fast also pointing here. When we move in a while loop, we say slow is equal to slow dot next. It jumps by one value. And fast is equal to fast dot next dot next. It jumps by two values. And if slow is equal to fast, so if ever they are both pointing at the same node, we can say cycle exists. So cycle exists in this linked list. So let's see for the example. Slow pointer moves, let's keep their values here, slow and fast. Right now both are pointing at 1. Now slow moves slowly, so by one value, slow dot next, slow comes here. So slow is now pointing to 3. Fast moves two values, so is 3, 5. 5 is now at 5. Slow then moves from 3 to 5. 5 moves by two values, so from 5 to 7, 7 to 3. So it came at 3. Then slow moves to 7, and then fast moves from 3 to 5 and 7. 7. At this stage, slow and fast are equal, a cycle exists. And this would happen in all the examples. So even if you consider another example just for sake, let's see, we have 1, or let's delete a little. Okay, we have 1, 3, 5, 7, 8. Okay, I have added one extra value just to showcase that this approach will always work. Okay, now again we'll do slow, fast. So slow is at 1, fast is at 1. Slow moves by one value, slow dot next, it reaches the value 3. Fast reaches the value 5. Slow then reaches the value 5, from 3 to 5. 5 fast reaches from 5 to 7, 8. So it gets 8. Slow goes from 5 to 7. Fast goes from 8 to 3 and then 5. Slow goes from 7 to 8. Fast goes from 5 to 7 and then 8. 2 jumps. So at this point, both 8 and 8, they matches. So we can say a cycle exists. This is one of the most common examples. We'll cover them in the part 2 as well. But hope these things clear out your concepts on linked list. Now, before moving forward, there is one very important thing for you all to understand. Okay, if you notice carefully, whenever we discuss that arrays are stored in memory in contiguous memory allocation, right? So if there is an array of size 4, it will get continuous 4 memory locations, right? 1, 2, 3, 4. And when we have a single linked list, what are we doing? We are storing data on one side and pointer to the next node. You can actually say that this is an array of size 2, because now all the time data and pointer to the next, they are in contiguous memory allocations. And here in this one we store the value of the data, that is 1, let's say picking up from this, and in the next one we store the address of the another node somewhere, right? But that is also an integer value. So even if I'm storing 1000 as an address to the next node, I'm actually storing an integer value. So you can say linked list, you consider a single linked list, is actually an array of size 2, right? And you just create more and more arrays and you add the values. Similarly, doubly linked list is an array of size 3. What if, now this is why linked lists are called the fundamental data structures. And if you see, arrays are the fundamental data structures as well, because arrays are being used to implement linked list. Let's say you have a very customized problem statement, okay, where you have to store phone numbers of people. You can actually create an array of 11 1 2 3 4 5 6 7 8 9 10 11 values, okay, and those values would be phone number, let's say 8 2 5 4 3, something like that, and the last one will store address to the next node that will again have 11 elements. The first 10 are the phone number value and the next one is the node to the next one. But since Java does not allow us direct access to the pointer and their addresses, this can be done with C. So in Java, we directly create them as classes. But again, as we create W-linked list classes where we store data, then next pointer and previous pointer, you can actually store data, data 2, data 3, data 4, data 5, any kind of data structure, and then next, previous, and anything. So if you see, all data structures emerges from linked list and linked list emerges from arrays again. Okay, I hope this helps. Let's move forward. So in the end, a few of the importance and significance of linked list. So dynamic memory allocation, since you know that insertion and deletion is very possible, very easy with linked list, the dynamic memory allocation is really good. Like in case of arrays, we need to know the size beforehand, but for linked list we can add elements after elements. Implementation of abstract data types. So if you see, linked lists serve as the foundation, as we just discussed, for implementing various other data types like stacks, queues, hash table. In fact, if you go for binary trees, they all come from linked list. Very efficient insertion and deletions, as we just saw, plus flexibility in data structures. By combining multiple linked lists or incorporating additional pointers, W-linked lists, we can create sophisticated data structures tailored to specific requirements, such as graph, trees, adjacency list, and the phone number example that we just saw, right? So linked lists are really, really important data structure when you are starting your journey on data structures and algorithm. Linked lists and arrays implementations, their theory, their fundamentals, and their understandings become very critical to this journey. Okay, so please go through the video again and understand them well enough. In the end, that's all from today's video, everyone. For the next video, we'll cover the examples on singly, doubly, and cyclic linked list, and we'll understand them via code examples. Thank you, everyone. For anything, please let me know in the comment section, and in the end, please like, share, and subscribe. Thank you.